All right, so it's Monday, and we're back here finishing up chapter 26, capacitors and energy storage. Quick reminder that the exam 2 will be next Monday during synchronous lecture on the 29th. Chapters 22, 23, 25, 26. So this is the last lecture for Unit 1. Another reminder, homework 8 is due Friday at 11:59 p.m. So get that turned in, and then I'll post the solutions Saturday morning for homework 8 so that you can have them to study for the exam. So we started off talking about this quantity called capacitance. And it's related to the ability of a device called a capacitor to store energy. And so, for example, here's a defibrillator, and here's a guy who needs it. And so some source, like a battery or something, is used to charge up a capacitor, and this energy is stored, and when the energy is needed, it's given back to the circuit, which is used to jolt his heart and hopefully bring it back into rhythm. And so capacitors are like energy banks. They're used to store energy. We deal with them all the time when you're dealing with touch screens on your phone and keyboards. You have two conducting surfaces here, and they're separated by a gap. When you press down on the key, that changes the separation, which changes the capacitance, and that is converted to a voltage which is used to cause the desired action, which is to create the ASCII code for the letter B. So what we started with yesterday, remember we talked about what a capacitor is. Remember, it's just two conducting surfaces, like two metal plates. And we've only been dealing with plates separated by air so far, but we're going to see that if we stick a chunk of insulating material in between here, we can increase the capacitance so that they can store much more energy. So we'll get into that in a little bit. And so with a capacitor, recall that we need some source of energy to separate this positive and negative charge here at the plate here, carry the positive charge over to the positive plate, and this separation of charge, we now have an electric field, and that gives a potential difference, and that leads to energy storage. We found that if you plug in the equation for the potential difference across the plates, it's linearly related to how much charge has been moved from one plate to another. So how much positive charge is separated from the negative and moved over to the positive plate. So the more charge we move over, the larger the electric field, the greater the potential difference. And so the potential difference is proportional to charge, and it's proportional to all these other constants, like how far the plates are separated by, and how much of the area of each plate is. And this stuff is all a constant that we lump into this variable that we call the capacitance. It's related to the ability to store charge. And so we derive that for a parallel plate with air gap, that the capacitance is equal to this permittivity of free space times the area over D. And when we plug that in, you see that the potential difference is related to the charge on the plates divided by the capacitance, which is a property of these capacitors. And here I got a picture of some. We'll get into them later. Here's a picture of some actual capacitors. They're made out of different materials. They have a different material in the gap. We'll get into what they are, but these are examples of what some of them look like. You've already dealt with this one without even knowing it. This is a tuner on your radio. You tune the capacitor by adjusting these plates, and that adjusts the frequency that your antenna can pick up, or more precisely, your circuit. So we all deal with capacitors without even knowing it. So if you look at the equation here and we solve it for the capacitance is equal to the charge on each plate, positive on the plus plate, negative on the other, divided by the voltage difference across the plate. And charge has units of coulombs, voltage has units of volts, and so capacitance has units of coulombs per volt, which is often called a farad, okay, and denoted by the letter F. So the capacitance describes how many coulombs of charge can be stored on the plates for every 1 volt difference between the plates that we charge it up. And a bigger capacitor can store more charge for every 1 volt than a smaller capacitor. So it's basically a measure of how much energy or how much charge can be stored by the capacitor. Now a farad, you'll see in a little bit, is a really large value. So usually we specify capacitance in units of microfarad, where a micro is 10 to the negative 6 farads, or we specify for small electronic circuit capacitors, we specify them in terms of picofarad. And you probably haven't heard the word pico, so it's 10 to the negative 12 farads. So most capacitors are specified in micro or picofarads. And if you look at this equation here, the capacitance depends on the geometry of the plates and the gap in between them. So it depends on how the capacitor is manufactured. So let's do an example here. So suppose that we have a 1 volt battery. Okay, that's a double A that should be 1.5 volts but is old. And we have a 1 volt battery, and we connect it up and we charge a 1 microfarad capacitor up. So we charge it up to 1 volt. So how much charge is stored on the plates? And then we're going to repeat that with a 2 if we charge it to 2 volts. And then finally we're going to repeat this if we replace a capacitor, the 1 microfarad capacitor, with a 2. Okay, so we plug in and we use the fact that the charge stored on the plates is the capacitance times the voltage difference, the potential difference between the plates. So if we have a 1 microfarad capacitor, that is 10 to the negative 6 coulombs per volt. And if we charge it to 1 volt, we have 10 to the negative 6 coulombs on the plates, and that's 1 microcoulomb. Okay. Now suppose we double the voltage. Well, I mean, you can see in this equation, if you double V, you're going to double Q. And in fact, that's the truth. You double it, you get 2 microcoulombs. So for every 1 volt on this capacitor that we charge it to, we get 1 microcoulomb of charge on the plates. So you can probably guess that if we charge it to 3 volts, you would have 3 microcoulombs. So the charge is proportional to how the voltage that we charge this up to. Okay? It's also proportional to this capacitance, C. So if we double the capacitance, instead of a 1 microfarad capacitor, we put in a 2 microfarad, then for the same voltage, we can store twice as much charge. So capacitance values basically are a measure of how much charge can be stored on the plates. Okay. So what if we want to make what if we want to store more energy? Okay, so if you have an air gap in between, and in practice we're limited as to how much energy we can store between the plates. But we can cheat a little bit, and suppose instead of an air gap, we put some polymer or waxed paper or some other insulating material, and we fill the gap between the 2 electrodes with an insulator. So my claim is that this will increase the capacitance by reducing the electric field in between the plates. Okay, so we'll get into why it does it, but let's just show first that if we stick a chunk of polarizable material, like a dielectric, in between the plates, that we're going to reduce the electric field. Okay, so here we do it. We stick a plate in, and you got a positive charge plate here and a negatively charged plate here. Well, that's going to separate this charge in the material, right? If it's polarizable, the positive charge on each molecule will be attracted to the negative plate. The negative charge will be attracted to the positive plate, and so you'll induce these dipole moments, or this separation of charge in the molecules of the material. And when we do that, you will create an electric field inside the insulator, right? So the electric field points from positive to negative, and so this induces an electric field inside the dielectric which points toward the right. And that field is in the opposite direction as the field on the plates, due to the plates, and it cancels a little bit of it out, or in some cases cancels a lot out. Okay, and so what we've done here, by sticking this chunk of insulating material in between the plates, is we've reduced the electric field between the plates. And the amount that the electric field is reduced is given by what's called the dielectric constant of the material. And that's a property of the material. We can look that up. And so, for example, a material with a dielectric constant of 2 will reduce the electric field by a factor of 2 relative to what it was before this chunk of insulating material was put between the plates. So in other words, the original field divided by the final field with it in is 2. It was twice as much before you put this in. And so let's look up what some materials are. Okay, vacuum, dielectric constant is 1, because if you put vacuum in, it's not going to change anything, so the field doesn't change. And you see that air is very close to vacuum. Now suppose you put Teflon and we fill the gap with Teflon. Well, that will decrease the electric field by a factor of 2.1, and then it goes up. Mica, rubber, 6.7, you've reduced it, all the way up to 80 if we put water between the plates. Now in practice, it's not a very practical solution to put water between the plates, and also if the water conducts, if it's not pure water, you can short the capacitor out, which is very bad. So in practice, we typically use a polymer or ceramic or wax paper or something, and so these little capacitors here, these little gold ones, have ceramic in between the plates. I think this one is a mica between the plates. And then some of these bigger ones can have an electrolyte in between the plates. So we can put something in, and that will reduce the electric field, and it'll increase the capacity for storing charge and for storing energy. So question is, how does it do it? You know, why does reducing the electric field increase the ability to store charge? Okay, well, if you recall, between the plates, the voltage, the potential difference between the two, is given by ED, electric field times the distance. Okay, if we reduce the electric field between the plates by sticking this material in, then we're reducing the potential difference between the two terminals. If we reduce the potential difference, then if you recall, capacitance is charge per volt of potential difference, and for the same amount of charge, we will reduce the voltage, and that increases the capacitance. So by sticking this insulating material between the plates, we're able to store a lot more charge. Per volt, we're able to store a lot more charge and a lot more energy. So what does that translate in terms of the formula? Okay, well, if the dielectric constant is E0, which is the original field divided by E that's in the plate, and that's equal to V over D, This was our original equation for the electric field without the material in between the plates. It's the charge Q on the plate divided by this permittivity, which is a constant of free space, times the area. We plug that in, we equate charge to voltage, and that constant of proportionality, recall, is the capacitance. And if you look here, it's exactly the same formula that we had for air, only it's multiplied by this dielectric constant, K. And so in other words, this capacitance can be much bigger if K is much bigger than 1. And so that's the purpose of putting either waxed paper or a polymer or ceramic or mica or something between these plates, is we reduce the electric field, which allows us to increase the capacitance or the ability of this capacitor to store charge. Okay, so this is the general equation for capacitance, and K the dielectric constant, is equal to roughly 1 with air, and then we get back our original formula. So if you look at the equation and you're designing a capacitor and you want to store a lot of energy, how do you do it? Well, the first is you have a large plate area A, right? And one way of doing this is you can actually make these at home. You can take 2 pieces of tinfoil, 2 long strips of tinfoil, and stick a sheet of waxed paper in between them. Okay? And then you have 2 conductors separated by an insulator. And since we don't want the capacitor extending all the way across our kitchen, we can roll this all up until it's in a nice little ball. And then actually that's what they do here, is they take this, and there's a large amount of area, and you keep rolling it up until it's in one little container here, which is more manageable. So we want a big area, we want large plates, we want a small thickness, right? So in other words, we want the plates close together with just a tiny gap of material, and insulating material in between. And then finally, we want a large dielectric constant. We want a material which will reduce the electric field by a lot. And so these 3 factors come into play when you're designing a capacitor. So why does it depend on that? Okay, so in other words, why does the capacitance depend on the area of the plates? Okay, well, it should be apparent, right? If you make the plates if you have a larger area, we can stick more charge on them. So bigger area, the capacitor can store more charge. Okay. Dependence on the gap thickness is a little tricky. I mean, it's not so easy to see, except if we go back to our favorite formula, V equals ED. If D decreases, meaning we put the plates closer together, that will reduce the potential difference. If we reduce the potential difference, we increase the capacitance. Okay. And the dependence on K is just what we discussed in the previous slides. If you reduce the electric field, you reduce the voltage, you increase the capacitance. Okay, so that's why your capacitance depends on the plate separation, the plate area, and on the insulating material that you stick between the plates. Okay. So what happens if you apply too much voltage between the capacitor? Okay. So these capacitors are rated. If we go back here, you'll see that this capacitor, God, I can't see this thing. Where is it? This one can handle 35 volts, it looks like. What happens if you put more than 35 volts potential difference across the capacitor? Well, the answer is the electric field is strong enough to break down the material in between, and so it will spark or arc just like a bolt of lightning, right? It'll conduct electricity. And for air, it's between 1 million and 3 million volts per meter, depending on the humidity. which is about 10,000 to 30,000 volts for every centimeter of gap. Rubber and glass are insulators, right? So if we stick these in between, it takes a greater voltage to break down these materials so they conduct. So rubber sticking an insulator between increases the breakdown voltage. Your author includes this. So we talked about how much charge is on the plate, but just a brief mention for how it's done probably doesn't hurt. And so here's your author's little charge escalator here. So we have the answer is you charge a capacitor using a battery, okay? And so the battery takes, originally both plates are neutral. So this battery, remember chemical reaction tends to move ions over to the positive plate. And so for each ion that it moves over, it leaves an electron behind, and so now you have an ion and an electron. Then it moves the second one over, and now you have 2 electrons and 2 ions. And now what happens then is, remember, you get an electric field pointing from plus to minus, and that starts to repel these ions that want to keep moving over. And so it takes more and more work as you pile more and more charge on. Each successive positive charge takes more work to move over to the positive plate. And so once you finally charge this thing up to the charge of the it charges up to the same potential difference is the battery voltage, okay? And that's because when this reaches equilibrium, the positive terminal of the battery is connected to the plus side of the capacitor, or the side that's positively charged, and the negative terminal of the battery is connected to the negative plate. And so since they're connected by wires, the negative terminal of the capacitor is at the same voltage as the negative terminal of the battery. The positive terminal of the capacitor is at the same voltage as the positive terminal of the battery, and therefore the potential difference when it's fully charged across the capacitor is the same as the potential difference across the battery. So we have now charged up the capacitor to the voltage of the battery. Okay, so 1 second here. Oh, I've got the demo coming up, and where is it? So the question is then, where does this energy go? Okay, so we're going to stop. I'll show you.
Whole bunch of them, electrolytic capacitor, and it's about as big as you'll ever see on a consumer circuit board. The energy stored in a capacitor is given by this formula. If I apply it to this capacitor, I can see that it can store a maximum of 11.2 joules. In certain circumstances, that's enough to do some serious damage. Now, the ultracapacitors I bought are 2,600 farads, and that's not a mistake, 2,600 farads, with a maximum of 2.5 volts. That means that one of these ultracapacitors can store 8.1 kilojoules of energy, which is a ridiculous difference. So let's see what a few kilojoules can do. Here I have the ultracap charged to 2.35 volts, and you can already see this thing means business. Let's start out by burning some soldering braid. Now let's melt an inductor. Here I'm shorting the cap across a 5-cent coin.
Whoa.
Wow, that beaver really took a pounding. And I thought it was fun to make these PCB traces light up like glow wire. Finally, let's make some random sparks again, just for the hell of it. And you know what's crazy? After all that, the cap is still charged to 1.7 volts. If you apply the capacitor energy storage equation before and after blowing things up, you can see that I used up 3.4 kilojoules of energy, so there's a lot left over. Now you might be wondering, how did I do all that with just 2 volts? If you take 2 AA batteries and put them in series, You get 3 volts with 2.5 amp hours of capacity, which is equivalent to 27 kilojoules of stored energy. That's more voltage and more capacity than the ultracapacitor has, and yet there's no way you could do all the things I just did with a pair of AA's. So what's the difference? The answer is a non-ideal property called equivalent series resistance, ESR for short. Batteries, capacitors, and a lot of other electronic components will have a small internal resistance, which limits the amount of current that can flow. For a typical AA alkaline battery, the equivalent series resistance is 120 milliohms. When you put a load on the battery, this resistance will cause a drop in voltage and it'll generate heat within the battery. For example, a low-power device like a TV remote control might draw 20 milliamps. This would cause a 2.4 millivolt drop, which is nothing, and generate 48 microwatts of heat in the battery, which is also trivial. But if I try to draw 10 amps from the battery, there will be an internal voltage drop of 1.2 volts, and 12 watts of heat will be generated within the battery. So at higher currents, the battery voltage is unreliable and things get hot enough to be very unsafe. Now let's see how the ultracapacitor would perform. This cap has a staggeringly low ESR of 0.7 milliohms.
Okay, that video was pretty lame, but since I'm not at campus and I don't have the stuff to do the demos with, it's about as good as we're going to do. But the gist of it is that this energy that goes into this work that the battery does, which goes into putting charge on the plates, can be given back to the circuit in a very quick pulse of energy, which can do good or bad. So that was the gist of it, is that these things can store a lot of energy that are given back when needed or not needed. So what we want to do next is to calculate the equation which relates the energy that can be stored in a capacitor to the voltage that we charge it up to. Okay, grab a couple sips of coffee, but not very interesting, but we need to do it. So the total work that the battery does is equal to the total work done in moving all of the charges over from the negative plate to the positive plate. So if, in other words, if we charge the voltage up to some voltage V and some final charge big Q, we want to calculate how much work is done, and that work is stored as electrical energy. Now, for a single charge, the amount of work is equal to Q times V, right? V is equal to the work per charge that must be done. Q is the charge. So that's the work that must be done for each charge. Okay, so we got to add all of these up to the total amount Q. So you might guess that we just plug in little q times v, and we say, oh, well, v is a constant, let's take it out of the formula, and we sum up all the charges that are moved over, and we get that the work done is equal to the total charge that we put over times the potential difference. Right? No, not right. And that's because the voltage is not constant. As we're adding more and more charge to the plates, the voltage becomes bigger, and it takes more and more work to move each successive charge over from the negative to the positive. Okay, so strictly speaking, we would do an integral to calculate this, but we're going to do something equivalent, which involves a little less math and gives the same result. So my claim is that we can use the average voltage as the value, which is just the difference between the initial voltage, which is 0 when no charge is there, and the final value, final voltage, which is delta VC. If we use the midpoint as the voltage to put in, that's an average value. Okay, and that'll be representative of the average conditions. Okay, so we could have done an integral, but we're not. And so if we put in that the work is equal to the increase in potential energy is the total charge times the average potential, and the average potential is 1/2 delta VC, we get 1/2 Q times delta VC is the work. Okay, now this is correct, but there's a more convenient way to put it because typically we don't know Q, but we can measure the voltage, and we can measure we know the capacitance. We can read it off the value, the component. So really, we did an integral. I tricked you, but we use what's called the mean value theorem, which you may remember from Calculus 2, which says that the integral, the area under the curve, is equal to the product of the horizontal distance, which in this case is Q, times the average voltage. So anyway, outside of that, now we can put in that Q is equal to C times delta V, and we plug that in and we get the most useful form of this equation, that the amount of energy that can be stored across the capacitor is equal to 1/2 times the capacitance times the square of the voltage that we've charged it up to. Okay. And this is a more convenient formula because we know or can measure these. Now, if you know Q and C but not delta V, we can go backwards and we can plug in delta VC as Q over C, and you get another expression. But most of the time, this is a more practical method. Okay, and so the total energy that can be stored by a capacitor depends on how much voltage you can put across the plates. Square it, multiply by the capacitance. And so whenever this energy is needed, it can be given back to a circuit in the form of a rapid, intense pulse of energy. So some examples are camera flash units, defibrillators, power supplies, and pretty much nearly every other device that requires a short, intense energy pulse. Okay, so the capacitors, again, you can think of as like an energy bank. We put money in the bank by doing work on it, the battery does work, and that money is there to be taken out when we need it in the form of energy. So let's do an example here. Suppose you have in a defibrillator, suppose we're using a 175 microfarad capacitor, and suppose we charge the capacitor up until the potential difference is 2240 volts. Okay, by the way, this is much greater than a typical capacitor like what I showed you before. Don't charge them up to this voltage. So what we want to first do is calculate the magnitude of charge on each plate when it's fully charged, and then we're going to calculate the energy stored in the charged up defibrillator. So let's apply this formula that the energy stored is 1/2 times the capacitance times the square of the voltage, and we do that. And first we calculate charge. We really don't need it, but just for kicks we did it. So I plug in C times V, and that's storing 0.392 coulombs, which is a fair amount of charge on these plates. Okay. So how much energy is stored? This should be U here. Somehow the U got lost. U is 1/2 CV square. You plug in 175 times 10 to the negative 6 farads, because it's 175 micro, which is 1.75 times 10 to the negative 4. You plug in 2240 volts and square it, and you see that 439 joules of energy can be stored in the defibrillator. They're stored across the capacitor. And that 439 volts is available when needed to hopefully jolt this poor guy's heart back to normal beating. So again, the capacitor is an energy bank. Okay, now suppose that we short this capacitor out. What do you think would happen here? So suppose we had that defibrillator, and suppose that we charged it up so there's 439 joules of potential energy stored. And suppose we accidentally touch the negative and positive plates with a screwdriver. Don't do this. In other words, we're forming a short circuit. So we're connecting both plates by a conductor. What do you think is going to happen? Well, the positive charge is going to want the easiest path over to the negative charge, and that path is going to be straight through your screwdriver or whatever metal you use to short these two together, and you're going to get a huge current going from the positive to the negative, and that's going to heat up the metal, which can cause a lot of damage to both the screwdriver and you if you're holding it. So this is, you may think it's funny, but it's not. People accidentally short capacitors all the time when they're going in circuits, and if you accidentally touch these two electrodes at the same time with a screwdriver while you're reaching in there, you can short this out and you can kill yourself. So don't do it, or if you do it, know what you're doing. Okay. So the last part of the unit here is often when we deal with circuits, we don't just have a single capacitor, but rather we have more than one of them connected in a variety of ways. And we'll get into why we do that when we start getting into circuits in the next two chapters. But what we're trying to do here is show that if you have several capacitors connected, we can model them as a single capacitor with some equivalent capacitance for which the circuit behaves exactly the same way as the real system, but is much simpler to analyze mathematically. In other words, it's much less complicated, but it does the same thing. So there's two different ways that we can put capacitors together, and then there's combinations of all of them are combinations of these two. And you're going to do these in lab. The first way is we can wire capacitors in parallel, okay? And if any of you have done home wiring, or you often hear, well, if we're going to wire these two circuits in parallel, or we're going to wire them in series. So wiring them in parallel is just a fancy way of saying that the positive terminal of one terminal of each capacitor, all of them are hooked up to the same point. So in other words, in the positive terminal of the battery in this case, okay? And for series capacitors, they're wired one after the other. So we're going to look at both of these in a little more detail in a minute and examine the consequences of wiring them in series and in parallel, okay? And we've already done series and parallel with batteries, right? If you hook batteries up in parallel and if you hook batteries up in series, you get a different voltage and a different current depending on how you hook them up. So we're going to do the same analysis but with capacitors. All right, so the first is if we wire them in parallel. Okay, so if we wire several capacitors in parallel, we just drew two here, but you can extend this to 3, 4, 5 of them in parallel. What that means is that one plate, all of the top plates, for example, here are connected together by wires, okay? So the top plate of capacitor 2 is connected by a wire to the top plate of 1. The top plate of 1 is connected by a wire to the positive terminal of the battery. And if you have a third, the second would be connected by a wire to the third. So in other words, all of the top plates are connected together by wires. And similarly, all of the bottom plates are connected by wires. And those are all connected, in this case, to the negative terminal of the battery. Okay, so what's the consequence here? Well, remember that if everything that's connected by conductors, so all of these have to be at the same potential. So the plus terminal of the battery is at one potential. That has to be at the same potential as the top plate of C1 because they're connected by a wire. Remember, the voltage, the potential's constant at all points across a conductor. So the top terminal of C1 is at the same voltage as the plus terminal of the battery. Then if you have them both, the top terminal here connected to the top terminal of the second one, they're connected by a wire, so they must have the same potential. And so all of these top plates are at the same potential as the top as the positive terminal of the battery. Similarly, all of the bottom plates must be at the same potential as the negative terminal of the battery because they're all connected together by wires. And so if all the top terminals are at the positive voltage of the battery and all the bottom terminals are at the minus voltage of the battery, the negative, then the potential difference across each of these capacitors must be the same as the potential difference across the battery. And in fact, you'll see when we deal with resistors and other things that any time that you connect several things in parallel, they all have to be at the same voltage. They all have the same potential difference. So in this case, the potential difference across all of them is the same. It's delta VC, which is just the same as the battery, the voltage across the battery. Okay. So what does that imply in terms of the capacitance or the ability to store charge if we wire two of them up in parallel? Okay. Well, if Q is the total charge supplied by the battery to both of them, and this should be Q1 plus Q2, typo, I'll fix it. And then we plug in what Q1 is. It's C1 times delta VC, and C2 is Q2, the charge on capacitor 2 is C2 times delta VC. Then the total charge supplied by the battery to the capacitors and stored on the plates is just Q. And since they have the same voltage, it's C1 plus C2 times delta VC. Now this looks exactly like the equation for a single capacitor, only the total capacitance is just the sum of the two capacitors in parallel. And so this equivalent capacitance is just C1 plus C2. Okay, and we can extend this on to several capacitors, but the main point is if we wire these all in parallel, the total capacitance is the sum of all the capacitances that are wired in parallel. So if you wire some of them up like this, you can create a huge effective capacitance and you can store a lot of energy. So wiring them in parallel increases the capacitance, which increases the amount of energy that can be stored. So put this on the cheat sheet, the equivalent capacitance, if they're wired in parallel, is just the sum of each of the individual capacitances. Okay. Now suppose we wire them in what we wire them in series. Okay, and series is just a fancy word for saying we start at the positive terminal here and we wire the first capacitor up. Then the first one is wired to the negative terminal of the first is wired to the positive of the second. And then if we wanted more in series, we could just keep daisy chaining them all along. And then we complete the circuit by hooking it back up to the negative terminal of the battery. Okay? And so what's the capacitance here? Do we make a bigger capacitance or do we make a smaller capacitance if we wire them in series? So to see this, we know that the potential difference across the capacitor, and by the way, I forgot to note here, we typically in circuit diagrams will draw capacitors as two parallel lines separated by some gap. And so this is just the circuit symbol for a capacitor. So sorry about that. I should have said that before. So we know that the voltage across capacitor 1 is Q over C1. And we know the voltage across capacitor 2 is the charge on its plates over C2. And so the claim is that the total charge on each plate has to be the same. Okay, why is that? Well, if you charge this top plate up to plus Q1, then you have to have an equal and opposite amount negative Q1 on this plate, on the bottom plate here. Okay, which means if it's connected by a wire to the second capacitor, there can't be any net charge here. If there were, then the positives and the negatives would get together and they'd quickly neutralize it, which means that the positive charge on this top plate here has to be the same as the negative here. and the positive here has to be the same as the negative on this end of the plate. And so in a nutshell, the charge on all of the capacitor plates has to be the same. So you're like, okay, what does that have to do with it? Okay, well, what we're going to do to calculate the equivalent capacitance is we're going to apply Kirchhoff's loop law. Remember, that says that the the potential differences as we go around a loop have to add up to zero, conservation of energy. So if we gain an amount plus E, where E is the EMF, or the battery voltage, across the first one, then we go across a wire, we don't lose any voltage if it's a perfect conductor. Then we lose some voltage delta VC because we're going positive to negative, and so we get a negative change in potential across the first. We go to the second one, we're going positive to negative, so we're going to lose potential across there. And when we get back to the start, we have to end up with the amount of potential energy that we started with. We can't gain or lose, and so the sum around the loop is zero. So we start with this equation. Then we plug in delta V as Q over C, and the Q's are the same. And we get that the battery voltage, or the EMF as your author calls it, is equal to Q, and this constant of proportionality is 1 over C1 plus 1 over C2, and we call that 1 over C equivalent. Okay, and so if we connect capacitors in series, to add them, we have to add all of their inverses, and then we hit the inverse button of the sum of these inverses to get the equivalent capacitance. So I think it's easiest to do a couple examples, and that is in fact what we're going to do to end this. But here's a formula summarizing pretty much the main properties of capacitors. The formula relating capacitance to the potential difference, the capacitance relation to the spacing between the plates D, the area, and epsilon naught, and then putting in insulating material, we just add a K in here. The equations for the series and parallel capacitances. So these are the gist, and then there's the formula for the energy storage. Is 1/2 C delta V squared. So as far as this set of notes, pretty much a lot of what you'll need on a test can be summarized by this slide. So let's actually calculate. Suppose we have 3 capacitors and they're wired in series. In other words, we wire them one after another, and this is your battery here. And so what we want to find is what is the equivalent capacitance. Okay, well, we know that if they're in series, we have to add the inverses. Okay, and so 1 over 6 microfarads plus 1 over 10 microfarads plus 1 over 16 microfarads. And when you hit all the 1 over, when you do 1 over, you get 0.329 inverse microfarads. Okay, then we hit the inverse button. 1 over 0.329 gives you 3.03 microfarads. And so in other words, these 3 capacitors in series behave like a single capacitor with a magnitude of 3.03 microfarads. In other words, the battery doesn't know the difference whether we've connected these 3 capacitors or a single capacitor of 3.03 microfarads. The battery and the rest of the circuit don't know the difference as far as the amount of charge and amount of energy supplied by the battery. So these capacitors behave as a single capacitor of 3.03 microfarads. Now what's true in this example, and is always true, is that the equivalent capacitance of capacitors in series is always smaller than the smallest of any of the individual ones. So in this case, 6 microfarads was the smallest of the series capacitors, and the equivalent capacitance of 3.03 is less than the smallest. Okay, that's always true. Okay, In parallel, where we just add the capacitances together, you can see that the equivalent is always bigger than any of the individuals, because when you add three positive numbers, the sum is always bigger than any of the numbers. So parallel capacit, when you wire them in parallel, you get a bigger capacitance. When you wire them in series, you get a smaller. Okay, so you might say, well, how stupid, why would we ever wire them in series? We'll get to that more in the next chapter. Now let's get to a little more complicated example here. All right, sorry. So suppose we have a more realistic circuit where we have two capacitors in parallel. So we hook the 10 and the 16 in parallel, and then we hook this combination in series with the 6 microfarad. So what we want to do is find the equivalent capacitance of this mess of capacitors here. So the first thing we do is we can calculate the parallel equivalent of these two. So a 10 microfarad in parallel with a 16 microfarad, we add the two capacitances. That's the same, you can replace this combination by a single capacitor of 26 microfarads. Okay? So now our circuit's looking a little simpler. It's not as scary to analyze as this. Now to calculate the total equivalent, now we have a 6 microfarad in series with a 26, so we have to add the 1/overs, the inverses. And then when we're done, we hit the inverse button on that, and we get that the equivalent capacitance is 4.88 microfarads. So in other words, this combination of capacitances here behaves similarly, or at least the battery doesn't know the difference between this combination and a single one of 4.88 microfarads. Okay? And you probably can tell that this last circuit would be much easier to analyze mathematically as far as currents and voltages than this one. So the whole gist of this is this equivalent capacitance simplifies calculations while still not changing anything as far as the behavior of the actual circuit. So you should be able to, after you're done with the homework and going through the book, you should be able to calculate the equivalent capacitances in series and in parallel. All right, well, listening to myself now, and you probably are too, so we're going to end it here. This is the end of Unit 2. And so your exam again is on Monday, and your homework is due Friday night. So stop by in office hours if you have any questions. Not many of you have been coming by, which isn't good if you don't understand what you're doing. So come by if you're having any trouble, and we'll go over it. So have a good day.